Yeah, I am doing that.
Yes.
Yes. So today we are going to see the assessment of pump and pumping system. So basically, we'll solve the numericals which are collected and which are been doing uh, which I have been doing since my energy auditing journey. So we'll do couple of numericals here, and then we'll see how the questions are asked in exam. What are the trick part in the pumps and pumping system questions? So basically, we'll see the first example. A chemical plant operates a cooling tower, cooling water pump for process cooling and refrigeration applications. During the performance testing, the following operating parameters were measured. Pump flow they have given 0.40 meter cube per second. Power absorbed is power 325 kilowatt. Suction head tower basin level is given H1 plus 1 meter. Delivery head they have given, means discharge head they have given H2 so 55 meter. Height of cooling tower they have given 5 meter. Okay. Motor efficiency is 88%. Type of drive is direct coupled. Density of water they have given 996 kg per mm cube. So first we'll understand the what are the data is given or what the data signifies. So when we were doing the, just a moment, I'll. Okay, when we were doing the pump and pumping system assessment, we understood that there are two, three data required for the assessment. So one is your discharge head, one is your suction head. So they have to calculate the total head. Then you require flow rate of the pump. Then you require total head. Then you require input power. So in this example, your flow rate is given, input power is given, but suction head is given as plus 1 meter. Means during pumping system we have seen that a center line of a pump is very important, where from where you are getting your input. Means if you assume, I'm not able to share it on whiteboard. Yeah, so this is your pump. This is your pump center line. If you are what
Pump center line, sir, is like mid of pump or header pipe you are talking?
no, mid of the pump. The particular eye of the pump is like pump. If you see the pump, this is a pump,
Okay,
and,
center of the pump,
and
like axis of the pump you're talking about.
yeah, this is eye line of the pump. It is called a center line of the pump.
Okay.
Yeah, during that center line of the pump, so your water suction level, if this is your cooling tower, let's say this assume your cooling tower, and you are connected, you are the cooling tower, and this is your pipe is connected here, and your water, this is like your water level. Okay, so water freely flows from basin of the cooling tower to your pump suction, and this is your pump discharge, right? This is your water flow.
Sir.
So yeah, so if water flows freely from here, this has given so your height, suction head. This is 1 meter, right? And your discharge delivery head is given as 55 meter. Okay, so this is your free fall. So you will not require any energy to pump this water. Your water will be freely available to the pump eye level. So your plus 1 meter is there. So during calculation, your free fall is calculated as 55 minus your suction head, means 1 meter. So 54 meter would be your total head. In this example, they have given height of cooling tower, but this data is not required, because whatever height of the cooling tower, water will flow from nozzles, then fills, and then it will store at basin level. So there will be not be any requirement of height of cooling tower if your water, like your water is in closed loop. This is your closed loop. Let's say this is your closed loop, and here somewhere your pump, some pump is somewhere here, and your water flows from here to here, and here is some your application water goes from here to application then gives back to your this. So your pump suction and discharge head both are required. So here there is a few loss of gravity or loss of flow. So for that 1 meter is height of the cooling tower is not required. If your water is like below water level, eye line level, water is falling from or water is pumping from below your eye line level, you need to get that height. Or if you want to discharge it to the 10th floor of the building, so and it is not closed loop, your height is required. Here your height is not, height of cooling tower is not required. So 5 meter is nuisance data in this question. So you need to ignore that part. Motor efficiency 88%, type of drive they have given direct coupled. So and density of the water is given 996 kg per meter cube. So your flow is given, head is they have calculated H2 minus H1, hydraulic power 0.40 means you have to take the hydraulic power in meter cube per second. Generally, hydraulic power is always given in meter cube per hour. So you have to divide it by 36,000, 3600 means hour to second. So 0.40 they have directly given, 54 we have calculated, 996 their density of water is given into H, sorry, rho Q G H. It's G means 9 acceleration due to gravity and divided by 1000. So your hydraulic power is 211 kilowatt. Understand this is your pump. This is your pump. Sorry, this is your input motor. After that, you have a shaft. Then you have a motor. You have a discharge. So this is your P in, input power. Then this is your electrical motor. And this is your pump. So this is your shaft. So here is your PS. This is your PH. So whatever input power is given. So
PS is pump shaft or pump supply?
shaft
Shaft,
power.
okay. And PH is head.
Hydraulic power.
Okay.
And P input is your electrical input power.
Okay.
So whatever input power would be there, so there will be loss in motor due to efficiency, low efficiency, or due to loss in motor, electrical motor. So there will be some of the loss means that is given in your efficiency. So 88% efficiency means 12% is your loss. Then some of that is transmitted through shaft to pump. Hydraulic power is converted. Then means your shaft power is 100% not converted into hydraulic power. So there is a pump efficiency. So this is also loss. So input, if you are given the input 100, if your motor efficiency is 0.88%, so 0.88 would 88 kilowatt would be transmitted here to the shaft. After that, pump efficiency, let's say 70%. So 88 into 70% means around 55 kilowatt will be transmitted here. So during that overall procedure, 45% will be loss. So understand, if you have given the input power is 325 kilowatt and you have given the motor efficiency 88%. So 325 into 88% means somewhere around 325 into 0.88 means 286 kilowatt is transmitted to the shaft. So your transmitted power is 286 kilowatt and your input power was 325 kilowatt. So your hydraulic power is given as 211 kilowatt. So understand that from 325 you are transmitted only 211 kilowatt. So 211 hydraulic power divided by shaft power is equal to your efficiency of pump means 211 divided by 286. would be
211 divided by
286.
211 divided by 286. Okay.
Yes, 286 would be from 325 kilowatt is your power input power here. You have given the input. Your motor efficiency is 88%, means you have lost 12% in this transaction. So 286 into 12, 88%. So 286 kilowatt is transmitted to shaft. So shaft power is 286 kilowatt, and your hydraulic power is 200 kilowatt.
So can you
So from
repeat it again? Sorry, I lost it. Like, can you start from P in and let me know once?
so P input power is given as 325 kilowatt,
Correct.
right? So
That is
from
power
that
absolute.
power absorbed by the motor. But
Okay.
your power absorbed by the motor is not directly transmitted 100%. There
Mhm.
would be some loss at the electrical motor due to lower efficiency of the motor. So
Mhm.
from that efficiency, you have got the uh,
88% efficiency of the motor.
88% efficiency of the motor is given. So
Okay.
from 325 into 0.86 88 would be your shaft power. Shaft power is equal to input power into efficiency of the pump, efficiency of the
280.
motor. So
Okay.
your shaft power would be 286 kilowatt. So
Correct.
286 kilowatt is your shaft power, and hydraulic power is 211 kilowatt. Between shaft and hydraulic power, your equipment is pump. So efficiency of the pump would be shaft power divided hydraulic power divided by shaft power. Input divided by output. Output divided by input. So your output is your hydraulic power, and input is your shaft power. So 211 divided by 286 would be
Divided by
74%.
73.77. Okay.
Yes, so round off is 74%.
Got
But
it.
understand, from 325 kilowatt, you are transmitting only 211 kilowatt. So if you want to calculate the system efficiency, so your motor efficiency is 88%.
Hmm.
Motor efficiency is 88%, and
Correct.
you have got the efficiency of the pump at 74%. So means 88 into 74.
88 into 74.
Yeah,
Okay.
0.88 into 74 divided by into 100 means your system efficiency is N motor, efficiency of the motor into efficiency of the
Percentage.
pump would be 65%. Means from 325, your output power is 200 kilowatt. Got it?
Okay, that is 65. Okay.
Overall efficiency is motor efficiency, because there are two transmitting equipments. One is your motor, one is your pump. So 325 kilowatt, whatever input is given, is transmitted to 111 kilowatt. So if you do 200 divided by 325, it would be almost similar as 65%.
Got it, sir. Got it.
Yes. In a municipality pumping system, water is pumped from the river to underground circular sump of 8-meter dia in the intermediate booster station. Flow measurements were carried out by level difference in the sump. Pump takes 10 minutes to fill 1 meter level of circular sump. Pressure gauges are not available in the pumping system. The discharge pipe is horizontal, 300 mm dia and 8 km long. Friction factor for the pipe is 0.006. The pump has a negative suction of 2 meter. The details of power measurement at motor are three-phase voltage 415 volt, line current 93 ampere, power factor 0.89. The efficiency of the motor is 0.90. As an energy auditor, work out of the following: flow rate of the pump in meter cube per hour, power drawn by the motor in kilowatt, total head developed by the pump, operating efficiency of the pump. So this is the question. So you have not given direct any answer or direct. You have not given the direct answer or direct data. So you have given the indirect format of the data. So if you want to solve that example, we need to understand what are the data they have given. So they have given diameter of intermediate booster station, means they have given the total volume capacity. Then they have given the difference, time difference, means 10 minutes to fill 1 meter level of circular sump, means they have given the difference between the level. So there is a hourly basis or minute time taken, the time taken as a parameter they have given. After that they have given the pipe diameter, discharge pipe diameter, and
Length.
length. So we have to calculate the frictional factor. From the frictional factor we have to calculate uh, uh, discharge head, and they have given the motor power. So flow rate of the pump, if you want to calculate flow rate of the pump, we need to calculate that pi by 4 d square. They have given your
Sir, I have a doubt. We are
okay.
actually pumping the water to a underground station from a different level.
Yes.
Why do we have a frictional factor actually? Like,
So they have given like that your pump has a negative suction of 2 meters, means from underground it is having suction, and your discharge head they have given the diameter of the pipe and length of the pipe, right?
okay,
So there are two heads in the pump. One is your discharge head, one is your suction head.
okay.
They have given the suction head as a negative 2 meter, means from the baseline or center line of the pump you are getting water from the negative side, means below the center line.
So technically, we don't have to minus it, it'll become an addition.
It would be an additional, because hd minus hs is formula to calculate the total head. So
Hmm.
your hd is in the positive side, because discharge would be always in the positive side.
Hmm.
So hd minus of minus 2, minus of minus 2 means it will be around uh, hd plus hs would be
But they haven't given the suction height. We
discharge.
have
They
to
have,
find
they have
that.
given the discharge, they have given the suction height, negative suction of 2 meters, they have given that.
Okay. Oh, we have to find out the total head and discharge of it.
Yes, yes.
Hmm. Got it, sir.
Okay. So if you want to calculate the flow rate, give me a moment. They have given the calculation of flow rate, means if you want to fill the water in uh, from the level of 1 meter, your water is rising 1 meter in 10 minutes, means in 60 minutes it will rise around you have given the diameter of the sump is 8 meter. So from the velocity you can calculate that, you can calculate your flow area. So from that diameter you can calculate the area of the sump. So it is pi by 4 d square, means pi by 4, 3.14 divided by 4 into d square is your 8, means area it would be 15.27 meter square. And your volume, if you want to calculate the volume is corresponding to 1 meter in 10 minutes, right?
Yes, sir.
So you are in every 10 minutes there is would be a rise in 1 meter. So 50.26 7 is your circle area. And if you want to calculate the height required, so 1 meter into 1 meter if you do, it would be in volume of the circle, it will be 50.27 m cube. For that 50.27 m cube, you are requiring 600 seconds, means 60 say 10 minutes you are requiring for to rise the 50.27 meter cube of the flow rate. So 50.27 divided by 600 would be around 0.0837 meter cube per second. So you are into 3600. So your flow rate would be 302 m cube per hour. Got it? Okay. Understand, this is your intermediate booster station, right? So this is your diameter of that intermediate booster station. So your diameter is 8 meter. They have given the diameter, and from that your 1 meter level, if you want to increase the 1 meter level, you will require that particular 18 minutes. So we have got the data of diameter is at 8 meter. So you can calculate from that diameter the area of the circle. But volume can be captured in, sorry, water flow can be captured in the volume. Means your intermediate booster station has something height. So for that height, we have given the level difference. So to rise 1 meter height means your volume is given. So 3.14 divided by 4 into 8 square is your area of the circle, would be 50 as a meter square, and your rise in height is 1 meter, means your volume is rise by 1 meter. So your total volume in 10 minutes you can fill up the 50.24 m cube of the level of the water. So for that 1 meter will require 600 seconds. So your flow rate is calculated in meter cube per second. After that, your calculation would be in meter cube per hour would be 301.44, means 302 m cube per hour. So this is understood.
Sir, I'm still confused with this.
Okay. So understand this is if you are able to see that particular drawing of that
Yes, sir,
particular
I can see the cylinder. Yes.
okay. So for that cylinder you have some area.
Correct, sir.
Water cannot be stored in circle. Water has to be, there would be some imagine a tank. Imagine a tank has some got some height.
Correct, sir.
A tank has got some circular area. So for
Mhm.
that tank, your circular diameter is 8 meter, right?
Okay, yeah.
And for that they have not given your height of the total height of the tank. So we don't need to calculate the total height of total volume of the tank, right?
Okay.
But they have given the level difference for 1 meter level increase in level. You will be require 10 minutes time. They have given the time.
Correct, sir.
So water would be filled in this level only if we assume that tank level is this much only, right?
Okay, assuming if the tank level is 1 meter randomly,
Yeah,
so what
randomly,
would
not randomly, because they have given the to fill the 1 meter, you require 10 minutes,
10 minutes,
right?
correct.
We need to calculate the flow rate. We
Correct.
don't need to calculate the total volumetric capacity of that particular tank.
Yes, sir.
Okay, so area is given 8. They have provided 8 meter dia, so you can calculate the area 5/4 d square.
Okay, okay.
Okay. After that, your to calculate the volume of that particular tank, you have given the 1 meter height.
Okay.
So water can be captured in volume. Means you have to calculate the volume of the particular cylinder. So area into height would be volume of that particular tank,
Okay.
right? area is your pi by 4 d square into your h. H is 1 meter for that moment. Got
Okay.
it? So pi by 4 d square into h is 1 meter. So our answer would be 50.24 meter square, meter cube. To get that 50.24 m cube of water in that particular tank, you would require 10 minutes. They have given the timing.
So I'm just seeing this solution itself. So pi d square by
Don't
4, and that is 60 minutes divided by 10 minutes. Is that so?
no, don't see that solution. I'm like
Okay.
solving in different manner.
Okay, done.
Okay, so your volume would be 50.24 in 10 minutes, right?
Correct, sir.
So you are for that 50.24, you are requiring 10 minutes means 600 seconds. So 50.24 divided by 600. Your volume of flow rate would be 50.24 by 600 means 0.08 meter cube per second, right?
Okay.
So 0.084 meter cube per second. And in your hour, your flow rate would be 50.84 into, sorry, 0.084 into 3600 means 302 m cube per hour. If we switch on that particular pump for an hour, your volume, total volume can be stored as 3082 m cube. Got it?
Mhm. Okay, sir. Got it.
Okay. In a 10-minute cycle, you can store the volume as 50 m cube, right? So you have got the flow rate of the pump is 302 m cube per hour. Then they have given the power drawn by the motor. So you have given three-phase voltage 415 volt, line current they have given, a power factor they have given, and efficiency of motor is given. So to calculate power drawn by the motor, if you want to calculate three-phase power, root 3 VI cos phi is the formula. So root
Mhm.
3 V voltage is 0.415, I is 93, cos phi is your power factor 0.89. So your power drawn by the motor is 59.45 kilowatt. Got it? After that, we need to calculate the frictional head, means dynamic head. They have given the all the data for to calculate the discharge head or dynamic head. So your they have given pump dia, pump length, piping length, frictional factor they have given. So to calculate the frictional head, we'll require 4 FLV square divided by 2 GD as a formula. So 4 in, but we have to calculate velocity first. We have not known the velocity of that particular uh, pumping system. So we need to calculate from the flow rate of the pipe. So your flow rate of the pipe is pump is 302 m cube per hour. You have given the diameter of the pipe, discharge pipe. So 302 m cube divided by 3600. So if you want to calculate the any volumetric flow, so your formula is area into velocity. Means any fluid is passing from the any particular enclosed pipe, it will be capturing velocity, and your enclosed area will provide the area to it will be given as volumetric flow. So to calculate volumetric flow, your calculations are area into velocity. So 302 we have calculated from the above data. 302 as your volumetric flow is equal to area, and velocity we need to calculate. So area they have given the discharge pipe as dia as 300 mm. So area would be pi by 4 d square. Pi by 4 into 0.30 square. So to calculate that, we got the velocity as 1.19 meter per second from that data.
Okay.
After that, we need to calculate the frictional head. So frictional head would be 4 into F as given as 0.006 as frictional coefficient. L is given, sorry, V is given 1.19, we have calculated 1.19 square, and 8 kilometer length of the pipe is given as 8 kilometer, means 8,000 meter. So divided by 2 GD, 2 into 9.81 into diameter of the point is 0.3. So you have calculated frictional head or discharge head as 46.2 meter. From that frictional head, you can calculate total head, means 46.2 minus of minus 2, means you need to work on the additional 2 meters. Your total head would be 48.2 meter, right? This is your discharge head to 46.2. Your minus 2 is given as negative suction level. Here they have given the pump has negative suction head of 2 meter. So your total head would be 48.2 meter. After that, hydraulic power would be rho QGH divided by 1000. So rho is volumetric flow is 302 divided by 3600, means you have calculated it in meter cube per second. Then 48.2 they have given as we have calculated as the total head 48.2, and then 9.81 is acceleration due to gravity. Into 1000 is density of water divided by 1000, means they have cancelled it. So your hydraulic power is 39.7 kilowatt. After that, we need to calculate shaft power, because your input power they have given, we have calculated as 59.5 kilowatt. We have calculated here. We have calculated this as a input power 59.5 kilowatt. After that, after that, efficiency of the motor is given as 90%. So your 59.5 into 0.9 means your shaft power is 53.55 kilowatt. So if you want to calculate the efficiency of the pump, efficiency of the pump would be hydraulic power divided by shaft power, means 39.7 kilowatt divided by 53.55 kilowatt. It would be roughly around 74.14%. Understood?
Yes, sir.
Okay. The centrifugal clear water pump rated for 800 m3 per hour was found to be operating at 576 m3 per hour with discharge valve throttled. The pump speed is 1485 rpm. The discharge pressure of the pump before the throttle valve is 2 kg per cm square. Gauge. The pump draws the water from some 4 meter below the center line of the pump. The input power drawn by the motor is 124 kilowatt at a motor efficiency of 92%. Find out of the efficiency of pump. If the normal required water flow rate is 500 m3 per hour to 700 m3 per hour, what in your opinion should be the most energy efficient option to get required flow rate variation? We'll solve the first two and then we'll go to third. They have given the data, a centrifugal clear water pump rated for 800 m3 per hour. This is rated data. This is not operating data. The operating data is 576 meter per hour. During our exam, we need to be very cautious to understand data first. If you write all the given data correctly, you can solve any question. But if you are confused between what is input data, what are the data given, you will be in trouble. So you need to understand your input data correctly. So your input data is 576 mp per hour. mp per hour is given as flow rate. Discharge pressure they have given 2 kg per cm square. Gauge means 20 meter head. And your suction head is 4 meter below the center line, means minus 4. And input power they are given as 124 kilowatt and motor efficiency is 92%. So if you want to calculate hydraulic power, same formula is applied here. At the discharge head, we can calculate 20 minus of minus 4 means 24 meter head as a total head. 576 divided by same formula can be applied here again and again. Your hydraulic power would be 37.67 kilowatt. But your input power is given as 124 kilowatt. Understand, this is very important. Your hydraulic power is 37 kilowatt only, and your input power is 124 kilowatt. There is a huge difference. Means your system efficiency is roughly around 31%. Means there is a 70% loss. Input power of the pump is given as 124. Your to calculate shaft power, you need require efficiency of motor. Your efficiency of motor is 92%. So your input power is 114 kilowatt. Your efficiency of the pump would be 37.67 divided by 114 kilowatt. Means your efficiency of pump is 33%. Understand? Your 800 m cube per hour pump is operating 576 meter cube per hour. Your discharge wall is throttled. Means there is a additional frictional resistance is given in the circuit. Despite that, your efficiency would be coming to 33% only. If your wall is not throttled, there you will be in trouble. Your pump is in trouble. So what they have done, they are throttling the wall. Means they have reduced the flow rate. So in that system, what are the possibilities, or what are the possibilities of energy saving? You, they have asked the question as 500 m cube per hour to 700 m cube per hour. Desired water flow rate should be between 500 to 700. What would be most energy efficient option? So we can use, we have seen the earlier, we can use multiple option to reduce your flow rates. So one would be throttling the wall, but it is not efficient because after throttling wall you are adding more resistance in the system, so your efficiency would be dropped. There is another is you can add uh, lower size impeller or trim the impeller, but you can get only fixed speed after that energy efficiency measure. But you want variable flow. So what is the best option to get variable flow? You can add variable speed drive, in the circuit. So your since the pump discharge requirement is between the range, not the fixed. If your fixed speed would be there, the solution would be trim the impeller or reduce the impeller size. But there is a variable flow requirement. So variable speed drive is your energy efficient option. Third question, what they have given, and what would be the pump shaft power, the most energy efficient option if the pump is delivering the flow rate of 550 m cube per hour? Means in the VFD, to deliver fixed speed of 550 m cube per hour, we need to fix the speed. Means we need to reduce the speed of the pump. So how to calculate the reduced speed? So there are affinity laws. N2 by N1 is equal to, sorry, N1 by N2 equal to N1, whatever the flow rate would be proportional to your flow rate of the pump. So your N1 is directly proportional to your flow rate, means Q1. So your 550 divided by 800 is equal to N1. N1 would be your 550, they have given the new speed, and 800 is your rated speed. So your N1 is need to be calculated. So 1485 is your original speed. So calculated speed of the pump would be 1021 RPM. Means you have reduced the speed of the pump. You are not affecting any. You are not affecting any other mechanism like throttling of the pump or bypassing the flow rate. So after that installation of VFD, you can run on fixed speed. After that, you have achieved 1021 RPM as your fixed speed. So pump shaft power would be 1000 RPM or 21 RPM divided by 1485 into cube into original power. Means original power was 114 kilowatt was your input power to the pump. So your hydraulic power would be 37 kilowatt only. After that, after reducing your flow rate from 800 m cube with BSD, you can save upon power from 124 kilowatt to 37 kilowatt. Means sorry, 114 kilowatt to 37 kilowatt. Means there is a significant amount of power can be saved with the help of variable drive. If your flow rate is far away from the actual requirement. Got it?
Yes, sir.
Okay. A centrifugal water pump operates at 30 m cube per hour and 1440 rpm. The pump operating efficiency is 65% and motor efficiency is 89%. The discharge pressure gauge shows 3.4 kg per cm square. The suction is 3 meter below the pump center line. If the speed of the pump is reduced by 25%, estimate the following: pump flow, power, pump head, and motor power. Assume motor and pump efficiency remains same at reduced speed. What they have given? They have given 30 m cube per hour as flow rate. They have given the 30 m cube per hour as flow rate, 1440 rpm as your speed. Pump operating efficiency is 65%, motor efficiency 89%. The discharge pressure gauge shows 3.4 kg square cm square as pressure, and suction is 3 meter below center line. So you need to reduce the 25% speed. Flow is 30 m cube per hour. Head developed by 34 minus of minus 3, 37 meter. Power drawn will be hydraulic power rod. From hydraulic power, you need to calculate shaft power. Shaft power, from shaft power, you need to calculate input power. So input power would be 4.65 kilowatt from the given data. But you are reducing your speed by 25%. You need to calculate the uh, resultant speeds. So your N1 by N2 equal to 30 divided by Q2. So your N1 was 1440 RPM, N2 is 1080 RPM. 30 is your original speed, Q2 need to calculate. So Q2 would be from calculation 22.5 m cube per hour. Head would be square of the change in speed. So 37 was your original head, 37 by H2 equal to 1440 divided by 1080 square. 1080 is your 25% reduced speed from original speed is 1440 rpm. So your reduced head would be 20.81 meter. If you are reducing the speed of any pump, your head would be reduced, your flow would be reduced, your flow would be directly reduced, head would be reduced by a square of that particular change. Then your power would be square of that cube root of the cube of the particular change. So your input power is 4.65 kilowatt. Second power in need to calculate. So 1440 cube divided by 1080 cube. So your new power would be 1.97, 1.96 kilowatt is your shaft power. So power drawn by the motor would be shaft power divided by efficiency of the motor. So is your 2.2 kilowatt. If you reduce your speed by 25% only, your reduction in power would be 4.65 kilowatt to 2.2 kilowatt, means approximately 2.4 kilowatt is saved. But you need to get that data correctly. What is your system head requirement, system flow requirement? If you are only capturing one of the data, means you are, if you are capturing only flow requirement of the system, but you are not attending, or you are not taking head as a consideration, you will be in trouble, because it is much important in your pumping system. Because if you are reducing the flow rate but your head is subsequently reducing, you cannot pass through the desired application, or your pressure drop across that particular desired application is much higher than the new discharge head of the pump. You will be in trouble, because you cannot transfer that particular fluid from a point A to point B if your head is not sufficient to overcome the frictional resistance of that particular application. Like heat exchanger, if your heat exchanger has own pressure drop of, let's say, 20 meter, and your piping and all this has a pressure drop on another 5 to 7 meters, your desired head should be more than 27 meters to deliver the flow rate across that particular system, because your system requirement is 27 meter, and your initially flow was 200 m cube per hour at 40 meter head, and you are reducing that particular flow rate, or uh, flow rate or head without consideration of any of the parameter, you can be in trouble because your flow rates cannot be delivered at desired locations. Another question is linked to that particular. Calculate the pressure drop in meters when the pipe diameter is increased from 250 mm to 300 mm for a length of 600 meters. Water velocity is 2 meter per second in 250 mm diameter pipe and friction factor is 0.005. So we have seen that earlier. If you increase the diameter of the pipe, your frictional head would be reduced because friction is directly proportional to diameter of the pipe. Sorry, friction is directly proportional to your, sorry, inversely proportional to velocity of the pipe, or we can say uh, uh, if your velocity of the pipe is going to increase, your you can see more frictional resistance in smaller size of the pipe. So to calculate the pressure drop, we need to calculate first in a 250 mm water diameter, particular diameter pipe. So to calculate that, 4 FLV square by 2 GD is given. So you have to given, but we need to calculate only pressure drop of 300 mm 300 mm diameter pipe. So velocity can be calculated from 250 mm dia pipe. To calculate that area into velocity, to calculate that we need to have the flow rate of the initial pumping system. So but the flow rate is not given in that particular second question. So these questions are not interlinked with each other. These are the different a part A is different, part B is different. So you cannot take the part A flow rate in part B to calculate that part B. So your initial flow rate was velocity was 2 meter per second in uh, 250 mm dia pipe. You need to calculate that V2 in 300 mm dia pipe. So your V1 divided by V2 is equal to area into means your diameter change into you need to calculate the diameter change. So 0.25 into 0.25 into 2. 2 is your velocity given divided by change in velocity is change in diameter is zero point 0.3 into 0.3. So your new velocity would be 1.39 meter per second. Velocity is directly proportional to your change in diameter. So your diameter is increased, so your velocity is going to decrease. Your new velocity is 1.39 meter per second. So to calculate that pressure drop of 300 mm pipe, your formula is 4 FLV square by 2 GD. So your 4 F is given as 0.05, length of the pipe is given as 600 meter, velocity we have calculated from uh, this particular equation 1.39 meter per second, and 2 GD is given. So your pressure drop with 300 mm pipe is 3.94 meter. Got it?
Yes, sir.
So in a commercial building, an energy audit recommended to bring down the cooling tower from the terrace to ground with a view to save energy in the pump. Details are given in the sketch below. Ignoring the frictional loss, will the measure save energy? Will this measure save energy? Explain the reason. So this is your cooling tower, which is located at terrace, and from that bottom you are circulating the pump. This is your closed loop, right? From your pump condenser, you are sorry, your from your pump discharge you are supplying to the condenser. From that condenser, it is circulating to cooling tower. After that cooling tower work is done from the basin, your free fall of the water is given to the pump suction. So this is closed loop. So height of that particular cooling tower matters or not, or the piping distance matters or not. If you are given the frictional loss as to ignore the frictional loss, does the height of the cooling tower or the location of the cooling tower matters to us in closed loop system?
No.
Because your discharge would be cancelled by your free fall of from the gravity, right? So whatever would be location, you have to do that much similar amount of the work. So from bringing cooling tower from terrace to ground, it will not actually save upon the energy if you don't have any frictional losses in the system. Considering the friction losses, but if frictional losses are not that significant, because in 56 meter, 56 meter of the pumping or piping would be roughly around having frictional loss as 2 meter, 2.5 meter. In 2 meter system would be roughly around zero point 0.1, 0.2 meter, 0.2 meter. So your frictional losses are not that significant in smaller or in that particular pumping system. But by bringing cooling tower, you will not save that much amount of energy. Frictional losses are not uh, in picture. You will be having same amount of energy. Will be requiring same amount of energy. So whatever will be the location will not save upon the energy by bringing cooling tower down to the pump level. That's why many commercial buildings or hotels like structures or commercial buildings, they usually place their cooling tower at the top of the building, whatever will be height of the building. They usually place that particular cooling tower there, because there are multiple factors affecting to that cooling tower. If we are not giving the good amount of ambient air or supplying the dust-free environment or good environment to the cooling tower, your cooling tower performance is going to decrease. So that's why their situation or location of that particular cooling tower matters in the cooling tower or in pumping system. So in this example, there will be no saving. But if this is a if this system would not be a closed loop, assume if this system is not closed loop, in place of that particular cooling tower, only a storage tank would be there. The height of that particular building or height of that particular from pump to that particular storage would have mattered if this is not closed loop.
So
Next
what
example.
other way around?
Sorry.
What if the circuit was other way around, like the pump to cooling tower kind of a concept?
Pump to.
Like now here, pump to condenser and it is going, the water from the cooling tower is a free drop.
Yes.
What if if the pump is switched, like you're pumping water to the cooling tower, then we have all these frictional losses and whatever coming up the efficiency.
No, I didn't get it. Your pumping losses, I didn't get it from there. Hello. If your pump is near to the cooling tower, that's That is your question. Hello. Hello.
Sir, sorry, am I audible?
Yes.
I think I have a network issue. So what I was talking about is, I hope this screen. So here basically like we have the pump and we are pumping it the other way. If we are switching it the other way, sir, like we are trying to pump the water to the cooling tower
Hmm.
on a higher side. So I guess then we have all this frictional losses and the efficiency might be like all this height difference from the cooling tower, which is whether it is on the terrace or ground floor, does matter a lot, right?
No, no. In closed loop circuit, your differential pressure does not matter in closed loop circuit because you are
Okay.
if you are ignoring the frictional losses.
Okay.
If you are not ignoring the frictional losses, it would matter, but it not be a significant amount.
Okay.
Yeah. In open loop, like if your cooling tower, this circuit is not of cooling tower, it is circuit of your domestic pumping. Like uh, this is your cross. Your water is not coming back here from here to the pump only. In your understand in your residential building, water from this point transfers to storage tank, and it is from gravity. It is going to user end, not again to the pump. It is
Hmm.
open loop. So height of that particular building matters in open loop. In closed loop, it is again water is circulated again and again.
Open loop, you're talking like if the water is going elsewhere.
Water is going to storage tank, and again storage tank is distributing to user points, not coming
Okay.
back to the pump side.
Got it, sir. Got it. Okay.
Yes, this is closed loop. This is only water is circulating, not water is consuming anywhere.
Hmm. Got it, sir. Yeah.
Next example, the following data of the water pump in a process plant have been collected. Flow is 70 m cube per hour. Total head is 24 meter. Power drawn by the motor is 7.2 kilowatt. Motor efficiency is 89%. Determine the pumping efficiency. Hydraulic power. We need to calculate hydraulic power. So it's a pretty straightforward question. You have given flow rate 70 divided by 3600. Total head they have given the 24 meter direct given 24 meter. Their power drawn by the pump is hydraulic power would be calculated 4.578 kilowatt. Power input to the pump is given as 7.2 kilowatt. Motor efficiency is 89%. So input shaft power would be input power into motor efficiency would be 6.48 kilowatt, and then pumping efficiency would be hydraulic power divided by shaft power. It's a simple question. Such questions can be asked for 5 marks or uh, like questions, odd questions. But nowadays they are more emphasizing on 10 marks, and from that you will be in 12 10 mark question. You will be having another data to calculate variable, VSD, speed drives, and all these things has to be calculated. This is a simple question. Next question is a centrifugal pump, water pump operates at 30 m cube per hour, 1440 RPM. So we have covered this up in above. So if pump is delivering 64 m cube per hour of water with a discharge head of 26 meter, the water is drawn by the from sump where water level is 3 meters below the pump center line. The pump drawn by power drawn by the motor is 8.89 kilowatt at 88% motor efficiency. Find out the pump efficiency. From that, we need to calculate the pump efficiency. So your flow rate is given. Your total head is 26 meter as discharge head, and sump level is below 3 meter from the center line. Means 26 minus of minus 3. Your 29 meter would be total head. Hydraulic power is would be 64 divided by 3600 into 29 into 100,000 into 9.81 divided by 1000. hydraulic power would be 5.0576 kilowatt. Pump shaft power would be 8.89 kilowatt into 0.88 would be 7.8232 kilowatt. So efficiency of the pump would be hydraulic power divided by shaft power. So your efficiency would be 64.65%. Head generated by centrifugal pump is independent of density of liquid being the pump. Head is directly proportional to your there are three parameters affecting the head of the system. One is your discharge or system requirement. If system requirement is let's say 20 meter, if you want to have a system requirement of 20 meter, whether you pump glycol, if you pump diesel, you pump water, your system head is not going to change. So your it is independent of density. You are in closed loop, it is not again going to change. If you are only just passing the water from underground basement tank to storage tank, your density is again not in the picture. There is a height difference. So it is independent of density of the liquid being pumped. It is the head is governed by the system or system requirements, not by the fluid, not by the power. The total system resistance of a piping loop is 50 meters and the static head is 15 meters at designed water flow. Calculate the system resistance offered at 75%, 50%, and 25% of the water flow. So in this example, there are two heads. One is your static head, means it would be in fixed head. It is due to height difference, and dynamic head is your dynamic head would be dependent on the flow rate. So your total head system resistance is 50 meters. From that, your 35 meter is your dynamic head, 15 meter is your static head. If you change the flow rates, your dynamic head is going to change only, not your system static head. At 100% flow rate, your dynamic head is 35 meter, but 75% flow rate, it is going to change. Means at 75%, your dynamic head would be 35 into that percentage flow rate, change in percentage flow rate would be 19.68. Static head is constant. So your total resistance would be 34.68 meter. At 50%, you are again going to change the dynamic head. So 35 into 50% flow rate and static head would be same. So your 8.75 plus 15, your resistance would be 23.75 meter. At 25%, it is again going to change 35 into 25 by 100. Means your change is dynamic head would be 2.19, but static head is still 15 meter because you are not changing the location of the pump or location of the, you are not changing the height of the discharge. You are just changing the flow rates. So you are by changing just mere flow rate, your dynamic head is going to change, not static head. So total head is summation of dynamic head and static head. So your resistance is going to change by 17.19 meter. Understood?
But definitely need a second shot.
Sorry?
I think you have to repeat this.
Okay. So understand, during our chapter, we have seen that your system is like this. Got it?
Okay, that's the graph. Okay.
Okay. Ignore the drawing part of graph
Okay, sir.
because I'm not used to this particular mouse and the cursor.
No
So
problem.
This is your static head, means your height difference, and this is your dynamic head. Got it?
Okay.
So static head is constant because it's constant throughout the speed variation. This is your flow rate. Here is your Q, and here is your H. So whatever flow rate is would be there, you are going to have same constant static head, but your flow rates are reduced. If you start from this point to this point, your flow rate is going to increase, so your head is going to increase. If start from this point to this point, your head is going to flow is going to decrease, so your head is going to decrease. So consider the example of a basement tank. It is transferring your water from basement to overhead tank. So from basement tank, assume that your height difference is 30 meter, right?
Yes,
Your
sir.
height your height is not going to change at any point of time. So you need to pump that water from 0 meter to 30 meter, right?
Mhm.
You are just playing around your flow rates. You are reducing your flow rate. Means what you are doing, you are just changing your flow rate by changing the RPM, changing in the variable drive, whatever you are mechanism doing. But you are just changing the dynamic flow. Means your velocity is going to change. So velocity is directly proportional. So your friction is directly proportional to velocity square. Got it? Your flow is reduced, means your velocity is going to reduce.
Correct, sir.
So if your friction is directly proportional to velocity square, if your velocity is reduced, your friction is going to change.
Correct.
Your dynamic head is going to change, right?
Mhm.
Static head is constant.
Okay.
You are not changing the height of the building.
Okay.
So only changes in the dynamic head, right?
Yes, sir.
Got it?
Yes, sir.
Okay.
So dynamic head is 35. Can I just
From
take it?
yeah,
35 meters. So we are multiplying square starting. That's a very large difference in dynamic head height, sir, from 75 to 25.
yeah. In the flow rate, if you are reducing the flow rates from
But
75 to 25, your dynamic head is going to change because you are reducing the flow rates. You are reducing the velocity, so there is no friction.
okay.
Assume a pipe. It is like assume a canal or assume a pipe. You are passing that water from that pipe. If it is open pipe, assume a was open pipe, and you
Hmm.
are passing water from one end to another end. Got it?
Yes, sir.
If your water level is like 50% of that pipe, so your water can flow from anywhere.
Okay.
There is no resistance in the pipe,
Correct, sir.
but your water level is more than your pipe,
Got it.
so there would be resistance to get into that particular pipe.
Mhm.
So that's a dynamic head. If your flow rates are on higher side, your uh, dynamic head, frictional head are going to increase.
Okay.
In example 11, they have given in a dairy plant, three numbers of cooling water pumps, identical in characteristics, are installed in a parallel to supply cooling. During normal operation, two of the pumps are operational, while one pump is on standby. all pump combination develop a discharge pressure of 3 kg per square cm square atmospheric. A is important. The installed water flow meter at the common header during an energy audit reading are pump number 1 to 545, 2, 3, 535, 31, 550. Means a combination of 1 2 gives 545 flow rate as effective flow rate of that particular pump. 2 3 gives 535 and 3 1 gives 550. Got it?
Mm.
They have given the power of 1 2 3, 33, 31.5, 5 kilowatt. Operating efficiency of 1 and 2 is 92% and motor efficiency of pump number 3 is 91.5%. So what they have given the data, they have given the flow rates of two pumps individual operating two pumps simultaneously. So we have to solve the individual pump flow, get the individual pump flow, individual pump efficiency, specific energy consumption, and what is the best pumping combination. So how to solve that particular equation? Assume pump number 1 and 1 2 3 as xyz. So x plus y equal to 545 m cube per hour. 2 and 3 means y plus z equal to 535. 3 and 1 would be x plus z equal to 550. So 1 2 3 equations are given
Mm.
by simple arithmetic. X plus y equal to 545 and y plus z equal to 535. If we subtract both the equation 1 and minus 2, you can eliminate y because y is common in 1 and 2.
Mhm.
So x minus z would be 10. Got it?
Yes, sir.
And there will be fourth equation would be developed. X minus z equal to 10 is apart from this three equation. Fourth equation is developed by us. So your x plus z and equal to 550 and x minus z equal to 10. So from this 3 and 4 equation, we can add this 3 and 4 means plus z and minus z would be eliminated. So from addition of 3 and 4, your x value, we have got the x value. X is 280. So from first equation x plus y equal to 545, we can get the value of y 265 and z as 270. So we have got the three pump values. X equal to 280 m cube per hour, y equal to 265 and z equal to 270. So individual flow rate we have got that. Understood?
Yes, sir.
Okay. So what are three? We need to calculate three. So we have done in this particular tabular format. So 1, 2, 3. Flow rate are 280, 265, 270. Discharge head they have given 3.4 kg cm square absolute. So absolute, from absolute we have to get the gauge pressure. Always display or pumping pressure is in gauge pressure, not in the absolute format. So from that absolute format, we have to negate the atmospheric pressure. So your discharge pressure is 3.4 kg square absolute. From that, we have got the gauge pressure is 2.4 kg square because atmospheric pressure is 1. So your discharge head would be 24 meter. So your total discharge head is 24 meter for all the pump because it's a common pumping system. Suction head is minus 3 meter. So your total head would be 27 meter. From this particular data, we have calculated the hydraulic power of the every pump. So 20.60, 20.22, 19.87. Power drawn by the motor they have given initially 33, 31.5 and 32.5. Motor efficiencies are also given. So your input power is calculated. Shaft power is calculated here. So your efficiency of the pump would be 67.9, 69.8, 66.8. Got it?
Yes, sir.
And specific energy consumption would be kWh per m cube. Means 30.36 divided by 280. To deliver 280 m cube flow rate, you will require 30.36 as 33 kilowatt as input power. From 233 divided by 280 would be your total flow rate. So your specific energy consumption would be 0.118 kWh per m cube, 0.119 and 0.120. So your pump number A, pump number 1, pump number 2, and pump number 3 has a like performance would be pump number 1 has better performance than other two pumps. Pump number 2 has better performance than pump number 3. So your combination would be pump number 1 and 2 would be best operating conditions. You can understand from here also. Pump number 1 and 2 delivers maximum flow rate. In pump and 1 and 2 would be delivering 545 m cube, and 1 and 3 would be delivering 550. Means your pump number 1 is always better in both the equation. So your operating best operating efficiency would be pump number 1 and 2 combination. A pump is filling in a rectangular overhead tank of 5 meter into 4 meter with a height of 8 meter. The inlet pipe to the tank is located at a height of 20 meter above ground. The following additional data is collected. Pump suction is given 3 meter below pump level. Overhead tank overflow line 7.5 meter from the bottom of the tank. Power drawn by the motor is 5.5 kilowatt. Motor efficiency is given 92%. Time taken by the pump to fill the overhead tank up to overflow level is 180 minutes. So assume a tank here. This is your tank. From this bottom, this is your overflow line. So means this is your, after this line your water is going to overflow. So this is your effective usage of the particular tank. Got it?
Yeah.
Height would be 7.5 meter. They have given the dimension 5 meter and 4 meter. So also height is given as 8 meter, but your effective height is only 7.5 meter. 0.5 meter in the above the overflow line is wastage. So 5 meter by 4 meter into 0.75 would be your total storage capacity. Means your volumetric storage capacity is 150 m cube. You can store 150 m cube of water in this particular tank. Got it? To
Yes.
fill to fill that total water tank, you will require 180 minutes. Means in 3 hours you can fill total entire tank. So means to fill that 150 m cube of tank, you will require 3 hours. So your flow rate would be 150 divided by 3. So your flow rate is 50 m cube per hour. Got it?
Yes, sir.
So from that 50 m cube per hour, you can calculate rest of the data. So from 50 m cube per hour, your head is given 20 meter above the ground. Your 3 meter below pump level means 23 meter is your total head. 50 divided by 3600 into 23 into 1000 into 9.81 divided by 1000. Hydraulic power, you got 3.13 as hydraulic power. Input given is 5.5 kilowatt. Motor efficiency is 92%. So your 5.5 kilowatt into 0.92. So your total efficiency, total input to the pump would be 5.06 kilowatt. So your hydraulic power 3.13 divided by 5.06 would be pump efficiency is 61.9%. So such examples are can be asked in your exam. You need to practice more to understand this particular utility chapter utility book, book number 3 and book number 2. You need to practice more to understand. You need to solve the previous question papers. You need to solve the solve numericals available with you in guide books or all these things. You need to practice more to get through this exam. List down 10 energy conservation opportunities in pumping system. So first is operate pump near best efficiency point. It is known because if you go away from any go away from any operating point, efficiency point, you will get to know that your efficiency is dropping. From the right hand side, your efficiency always drop. In the low left hand side, your efficiency always drops. Modify pumping system and pump losses to minimize throttling. This is if you are throttling, you have seen the example above example. If you are throttling the pump discharge, your power would be on a higher side. But if you are providing variable drive, your power is going to decrease. Means your throttling is your loss in energy because you are creating additional resistance. Adapt to wide load variation with variable speed drive or sequence control of multiple units. Means if your flow rate is your required flow rate is 500 m cube per hour to 700 m cube per hour, you can adopt variable speed drive because you are not bound by a single fixed speed. You have to variable flow rates, so you can save upon that particular variable powers also can be achieved. Use booster pumps for small loads requiring higher pressure. If like booster pumps in a multiple effective operator, there are multiple floors. In first floor you require 100 m cube, in second floor you require 100 m cube, but in third floor you require 20 m cube only flow rate. So you are in third floor, you require a lower amount of flow rate, but to get that particular third floor requirement, your pump has to do more work. 220 m cube per hour has to circulate for the entire three floors. Means your total flow rate is governed by third floor. So your 20 m cube per hour flow rate can be used by given by the booster pump in the line. So your entire pump has need not to do more work. Your first and second floor can be catered by main pump, and your booster pump can deliver only third floor pumping requirement. Increase fluid temperature differential to reduce pumping rates in case of heat exchanger. Means MCP delta T, you can increase delta T. So your mass flow rate can be lowered. And if mass flow rate is lowered, your work need to be done is getting lowered. Balance the system to minimize flows, and reduce pump power requirements. If your system is not requiring 700 m cube per hour, your system requirement is 500 m cube per hour, you need not to circulate that to 100 additional. You can change your pump, you can change your piping system. That will anyways going to save upon more energy than pumping or throttling or using any other mechanism. Avoid pumping head with a free fall return gravity. Use siphon effect to disadvantage. Means your free fall has to be captured in your pump suction. So you can use siphon effect. Means in cooling tower we have seen the example. If you free fall from that cooling tower, terrace cooling tower to a sump, and then again pumping to same loop, your free fall would be disadvantage. Your
Yes,
siphon
sir.
effect has to be used in the circuit. Conduct water balance to minimize water consumption. Means if your water balance or your water requirements are known, you can minimize your water consumption. Avoid cooling water recirculation in DG set, air compressor, refrigerant systems. All this recirculation can be avoided if you have a multiple set of chillers, 1, 2, 3, 4 chillers, and your operational are two chillers are standby. You can close down the walls of that particular chillers. You need not to circulate the water in from that particular chillers. So your pumping power can be significantly reduced. In multiple pump operations, carefully combine the operation of pump to avoid throttling. Means during your parallel operation, you need to be careful that your all pumps are of similar capacity, similar head, similar specifications. Replace old pumps by energy efficient pumps. You can see that 45% efficiency pump and 60% efficiency pump, there would be 15% saving can be achieved from old pump to new pump. In the case of over design pump, provide variable speed drive, downsides, replace impeller or replace with correct size pump for efficient operation. We have seen the example. Optimize number of stages in multi-stage pump in case of head margin. If your head margin in multi-stage pump, what happens in boiler feed pump? Your multi-stage means your pressure requirement is tremendous. In boilers, pressure requirement are like 400-meter pressure requirement. So your pump operate at 400-meter. You need to provide that 400-meter head. But your flow rate requirement is marginal, means your 10 TPS, 20 TPH, means 20, 10 meter cube, 20 meter cube at 400 meter. So if your operational head is around 250 meter and you are providing a flow rate, you are providing a pump of 400. So your 150-meter head is wastage. So your power is wastage by 150-meter. So you can provide that lower or you can reduce the staging of that particular pump. Reduce the system resistance by pressure drop assessment and pipe sizing optimization. You have seen that 250 dia and 350 dia. There would be a significant frictional loss in both the cases. If we increase 300 dia, so your frictional losses are going to decrease. Ensure adequate NPSH at the site of installation, means your net positive suction head has to be available. If what is required, that pump has to be available with that particular NPSH. After that, if you don't provide that NPSH to the site, your pump will get at cavitation. Ensure availability of basic instrument of pump like pressure gauge, flow meter. So from that you can get actual what is flowing, what is required. So you can evaluate the pump by your own. Stop running multiple pumps, add an auto start for online spare or add a booster pump in the problem area. Means if your pressure requirement of particular section or particular requirement is on higher side, you can add a booster pump to that. You need not to have entire pumping system to dictate by that particular smaller application. Your you can save much power in that particular application, or you can have multiple pumps running and your water flow requirements are variable. You can add a stop on off control to that particular system with the flow feedback of that particular flow what is requirement. Repair seals and packaging to minimize water loss by dripping. So your entire any water loss in the system is your loss in the system. So your if your seals and glands are from next to the pump, so your water is getting lost, you need to add more makeup water in the system, so your loss is to be going to be huge. These are some energy efficiency or energy conservation opportunities in pumping system. Hope I have clarified all the doubts or all the questions carefully. So these are the type of the questions you can get in your exam.
Okay, sir.
So I'll be sharing all the documents with coordinator as these were my last lecture in this particular batch. So I'll be sharing all the three chapter I have covered for your batch. I'll be sharing that PPTs and all these things to coordinator. You can get it from there. Practice more. Practice is the key. Your exam is 28th or 29th September, right?
हाँ सर.
So you have 10 days to practice. You start the practice.
Sure, sir. Sure.
Yeah, because book number 2 and book number 3 are of more practice, and book number 1 is of theory. So you need to understand the theory part of it. So you can you can write any theoretical part. But for book number 2 and 3, you require particularly understanding of that particular problems and all these things. So start practicing. Start at least 3 to 4 question papers, previous question papers, try to solve that.
Okay, sir. Done.
Yes.
At least that would cover major different kinds of problems that would come up.